Go out to your garage, find a wide rubber band, and stretch it hard and fast. Now press it to your upper lip. Warm. Let it snap back to its resting length and press it again. Cool. That's it. That's the whole trick. You just ran a refrigeration cycle with 2 hands and a piece of rubber. And a lab in Maryland has spent the better part of a decade figuring out how to do that same thing with metal, millions of times over, inside a box in your kitchen. Because the box in your kitchen is older than you think. Not the model, the idea. The refrigerator standing behind you right now runs on a principle patented in 1834 by a man named Jacob Perkins, born in Newburyport, Massachusetts, who built a machine that could pull ice out of thin air on demand. Everything since has been trim. Better insulation, better seals, an ice maker in the door, a screen that tells you the water filter is expiring. But the heart of it, the part that actually makes cold, is a 19th century concept that predates the light bulb, the telephone, and the internal combustion engine. You have a machine in your house that is older than powered flight, and you paid $2,000 for it. If you like this kind of thing, hit the like button and subscribe, because it genuinely helps, and there's more coming. Here's what's actually happening in there. A pump called a compressor squeezes a chemical gas into a tight space. Squeezing anything makes it hot, same as the end of a bicycle pump getting warm in your hand. That hot gas runs through the coils on the back or underneath, dumps its heat into your kitchen, and condenses into a liquid. Then the machine lets that liquid loose into a wider space, and when it expands, it goes cold and hungry, pulling heat out of the air around your milk and your leftovers. Then it does it again and again. Every 8 minutes or so for 15 years, in the dark, while you sleep. It's an elegant system, and it built the modern world. Take vapor compression out of American life, and the country stops working inside of a week. Grocery distribution collapses. Hospital pharmacies lose their inventory. Half the map becomes unlivable in August. It is arguably the most important invention nobody ever thinks about. It also has 2 problems that 190 years of engineering has never solved. The first one you can hear. It's the compressor. It's a small engine with moving parts, running around the clock, 3 feet from your food. Moving parts wear, bearings loosen, seals fatigue. If you've ever had a fridge die at 11 years old and had a technician tell you it's cheaper to replace than repair, you've met this problem personally. The second problem you can't hear or see, and it's the bigger one. It's the gas. Refrigerants live sealed inside those pipes, and sealed is doing a lot of work in that sentence. They seep at the joints. They escape during service. They vent when the unit gets scrapped in a yard somewhere. And some of them are genuinely destructive. R-134A, the workhorse refrigerant of the last generation, carries a global warming potential roughly 1,400 times that of carbon dioxide. 1 pound of it doing the work of 1,400 pounds of tailpipe exhaust. Now multiply that across every fridge, every freezer case, every car cabin, and every rooftop chiller on every strip mall in America. The federal government already conceded the point. Under the AIM Act, passed in 2020, the United States committed to phasing these high-warming refrigerants down by 85% over 15 years. That law exists, the clock is running, and the replacement chemistry is not comfortably better. The leading alternatives are variously flammable, higher pressure, or breaking down into compounds regulators are already uneasy about. So the country has legislated itself into a corner. It has promised to stop using the working fluid the entire cold chain depends on, without a clean substitute to drop in its place. Which forces an uncomfortable question. What if the answer isn't a better gas? What if the answer is no gas at all? Which brings us back to your rubber band. That warming and cooling effect is not a novelty. An English scientist named John Goff described it in 1805. James Joule quantified it decades later. It's called the elastocaloric effect, and the physics is almost insultingly simple. Deform certain materials and you force their internal structure into a more ordered arrangement. Order releases heat. Let them relax and the structure falls back into disorder, and disorder absorbs heat. It takes it from whatever happens to be touching it. No gas, no leak, no compressor, just a solid that gets cold when you stop squeezing it. For a century and a half, this stayed a classroom demonstration, because rubber can only move so much heat and it degrades in weeks. Nobody had a material tough enough to do it 10 million times without shredding itself. Then in 1959, a metallurgist named William Buehler was working at the Naval Ordnance Laboratory in White Oak, Maryland, trying to develop a better missile nose cone. He was alloying nickel and titanium. What came out behaved like nothing anyone had handled. Bend it and it sprang back. Heat it and it returned to its original shape, as if the metal remembered what it was supposed to be. They named it for where it came from: Nickel Titanium Naval Ordnance Laboratory, nitinol. An American invention, funded by the American military, and today it sits inside heart stents in millions of chests, inside eyeglass frames that survive being sat on, inside aerospace actuators. But its most interesting property was the one nobody had a use for at the time. Squeeze nitinol and its crystal structure snaps into a tighter phase and it heats up. Not a fraction of a degree, tens of degrees. Release it and it drops just as hard, drinking heat out of everything around it. That's a rubber band with the strength of aerospace metal. That's a refrigerant you can hold in your hand and drop on the floor. The Department of Energy noticed. In a landmark federal assessment of alternatives to vapor compression, analysts ranked elastocaloric cooling at the very top of the non-vapor compression technologies with real potential to replace the compressor. Not one option among many, the top of the list. So why isn't there one in your kitchen? The material's been around since Eisenhower. Because for 50 years, every machine anyone built out of it destroyed itself. Here's the wall. The instinctive way to work nitinol is to pull it. Take a wire or a thin ribbon, stretch it, release it, harvest the cold. And it works beautifully for a few thousand cycles. Then it starts to fail. Think about what pulling actually does to metal. Any tiny flaw, a microscopic void, a rough spot, a grain boundary, becomes a stress concentration. Pull, and that flaw opens a hair. Release, and it closes. Pull again. Every cycle widens it a little more. It's the same reason you can snap a paperclip by working it back and forth 20 times when you could never snap it in a single pull. Metal doesn't usually fail from force. It fails from repetition. Now consider what a refrigerator actually demands. Continuous cycling for 10 to 15 years. That isn't thousands of cycles, it's tens of millions. Early prototypes were hitting the end of their fatigue life after a few weeks of continuous running. Researchers would build a beautiful machine, switch it on, and watch the one component doing the actual cooling develop hairline cracks and shear apart. There was a second wall right behind the first. Nitinol needs enormous stress to trigger the phase change, which means a serious mechanical drive. Engineers were pouring energy in to strain the material and getting back a disappointing fraction as usable cold. Next to a compressor that industry had been optimizing since the 1880s, the efficiency numbers were embarrassing. By the 2000s, elastocaloric cooling had a reputation. Gorgeous physics, broken engineering. A technology that could chill a small volume very impressively right up until the moment it tore in half. Then a team at the University of Maryland, working with the National Laboratory System under materials scientist Ichiro Takeuchi, asked a question so simple it almost sounds like a joke. What if we stop pulling it? Their insight was about the direction of force. Cracks propagate under tension. Pulling opens flaws. Compression does the exact opposite. It presses them closed. Squeeze the metal instead of stretching it, and the microscopic voids that would have grown into fractures are being clamped shut on every single cycle. So instead of thin strips pulled apart, they used nitinol tubes and drove them in compression, hydraulically, along their length. Same phase change, same heat in, heat out, completely different failure behavior. The results, published in the journal Science, were the moment the field turned over. The compression-driven system didn't just last longer, it hit a material's coefficient of performance far past anything elastocaloric devices had managed, into territory where this stops being a curiosity and starts being a competitor. And it produced temperature spans wide enough to matter for real refrigeration, not the handful of degrees earlier rigs managed. Picture the architecture. A bundle of thin nitinol tubes standing like the barrels of a revolver. A hydraulic driver compresses them, they heat, and a loop of plain water, the safest working fluid on Earth, carries that heat out to the coils. The driver releases, the tubes snap toward their remembered shape and go sharply cold, and the water loop runs back through to collect that cold and deliver it to the compartment where your food sits. Notice what's missing from that description. No refrigerant gas, no regulated chemical of any kind. If the entire assembly ruptured on your kitchen floor, the environmental consequence would be a puddle. And at end of life, you don't have a technician evacuating gas into a recovery cylinder. You have nickel and titanium, and both go back into the supply chain. Now, be honest about where this stands. There's a version of this story that promises you a gas-free fridge by Christmas, and that version is not true. These are prototypes and pre-commercial units. Impressive ones, not products. The obstacles are specific. Nitinol isn't cheap. The alloy has to be melted under vacuum because titanium will grab oxygen straight out of the air and ruin the composition. And the nickel ratio has to be controlled so precisely that a fraction of a percent shifts the temperature where the whole phase change happens. Compressors are commodities stamped out by the tens of millions. Precision tube bundles are not. Second, you've replaced the compressor but not the need for force. Something has to squeeze those tubes hard, millions of times, in a sealed box in somebody's house, and that driver now inherits the durability burden the nitinol just escaped. Third, no manufacturer ships anything into American homes without years of hard survival data with warranty exposure attached. And fourth, the incumbent is a genuinely excellent machine, backed by a century and a half of manufacturing scale. Beating it in a lab is one thing. Beating it on cost per unit of cooling on a factory line is the actual contest. But none of that erases what happened. A 50-year wall came down because somebody stopped pulling and started squeezing. That's what most breakthroughs actually look like. Not a new law of physics. A change in direction that finally makes an old one usable. And sit with the symmetry for a second. An American in Massachusetts invented the machine that made coal a utility. An American Navy lab in Maryland accidentally invented the metal that might end it. And a university team a few miles down the road found the one direction of force nobody had properly tried. Which leaves the interesting question. The compressor isn't just in your kitchen. It's in your truck, your office ceiling, the data center outside town, the walk-in cooler at your grocery store. If this scales, which one goes quiet first? And which one are you actually going to miss the sound of at 2 in the morning? Tell me in the comments. And if you want the next one to find you, hit like and subscribe.